Hello everyone, welcome to lecture number 3 of this third week, and in this lecture we will explore Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem has importance in real numbers, and we will see that how this will play the applications of this Bolzano-Weierstrass theorem in a number theory, and not only in number theory but in a order completeness and order completeness of this and so on, right. So in this lecture we will cover every sequence of real numbers has a monotone subsequence, some of those examples, and then Bolzano-Weierstrass theorem, and then examples. I will try to give you the analytical proof of those theorems, but if you do not understand due to subcomplexity of this analytic proof of this theorem, then try to go through the examples, and one by one examples will boost your confidence as well as the concepts regarding the Bolzano-Weierstrass theorem, right. So the first theorem to prove this Bolzano-Weierstrass theorem, let us have the basic one. The first one says that every sequence of real numbers has a monotone subsequence. Give much more importance on the statement of the theorem. What the statement? The statement says that every sequence of real number. So you will choose any sequence an, then it has a monotone subsequence. It does not say that every subsequence is a monotone. No. You may find out that a sequence has a monotonicity. A subsequence of that sequence has a monotonicity, right. So be aware about a monotone subsequence and every subsequence is a monotone. Both are the two different things, and the statement only says that if you have a real sequence, there must exist a monotone subsequence. So I am going to prove the same thing, right. So let have the collections the natural number n s and name it s such that xm is greater than xn for every m is greater than n. That means s is infinite and their terms are n1, n2, n3 and so on. Then the sequence xn1, xn2, xn3 will become a monotonically increasing sequence, right. So xn1, xn2, xn3 is a monotonic increasing sequence, and that means it become a monotonic increasing subsequence. If s is finite, then there exists n1 such that n is less than n1, so n1 is greater than n for every n belongs to that s, because we have already defined s is the collections of all those natural number n such that xm, the sequence xm, must be greater than xn for each m is greater than n, what we have already defined, right. So if s is finite, then there exists n1 which is greater than n. Since n1 does not belongs to s, whatever we have said, right, then there exists n2 greater than n1 such that xn2 is less than xn1, and as it continue, as n2 does not belongs to s, then there exists n3. If n3 does not belongs to s, then there exists n4 such that xn3 or xn4 is less than xn1, it is less than xn, right. So that will makes us xn3 is less than xn2 is less than xn1. That will also give us xn4, xn3, xn3 is less than xn2 is less than xn1 and so on, right. So that will make that this is a monotone subsequences, right. So that is the proof that we have chosen any sequence of real numbers and each has a monotone subsequences. So consider the sequence minus 1 by power n divided by n, and possible subsequences are x to n. So find out so let me explore this sequence first. So the first term is minus 1 by 1, 1 by 2, minus 1 by 3, 1 by 4, minus 1 by 5 and so on, right. And if I choose the x2n, that means the even index number, this one. So this will makes me 1 by 2, 1 by 4, 1 by 6, 1 by 8 and so on. And obviously this is a monotonically decreasing sequence. So this is a monotonic decreasing sequence. Similarly, if we choose odd index numbers, odd index terms of this sequence, that collections makes a subsequence. And let me give you that number. So this is minus 1, minus 1 by 3, minus 1 by 5, minus 1 by 7 and so on, right. And obviously it is a monotonically increasing sequence, and that's why a sequence may have the monotone subsequences. So if you look very carefully of these subsequences, structure of these subsequences, you will see that even a sequence is given, the sequence may have a monotony increasing or may have a monotony decreasing. And that's why the statement of the theorem says that every sequence of real numbers has a monotone subsequences. Now consider this one, n in minus 1 by power n into n. So what will be the terms? This term is minus 1, this is 2, minus 3, 4, minus 5, 6, minus 7 and so on. Look at all even index terms. So what will be the even index terms? 2, 4. So here it is. So 2, 4, 6, 8, 10 and so on. And what it will be? It is a monotonically increasing subsequences. But look at the odd index terms. This will be minus 1, minus 3, minus 5, minus 7, minus 9, minus 11 and so on. And this is a monotonically decreasing subsequences. So that means the both are possible for a sequence. So a sequence of real numbers may contain the monotonically increasing subsequence or may contain monotonically decreasing subsequences. Now consider examples 3. So minus 1 by power n plus of 1 by n. Now firstly we have to write the terms. So what will be the terms? Here these are the terms. The first term is minus 1 plus of 1. So what will be the first term? First term is coming to 0. The second term, that is 1 plus of 1 by 2 is equal to 3 by 2. And the third term becomes minus 1 and plus of 1 by 3. So this will be minus 2 by 3. The fourth term, that fourth term is equal 1 plus of 1 by 4 is equal to 5 by 4 and so on, right. So the sequence can be written as 0, 3 by 2, minus 2 by 3, 5 by 4, minus 4 by 5, 7 by 6 and so on, right. These are the terms of the sequences. Now if I choose the positive terms only and if I choose the negative terms only, so that means we are looking for positive terms and negative terms, and both are the subsequences of this number because we are going to retain their orders as well. So we are looking for 3 by 2, 5 by 4, 7 by 6 and so on. It is a monotonically increasing sequence, right. So this is a monotonically increasing sequence. But look at the negative terms. So what are the negative terms? It's started with minus 2 by 3. So minus 2 by 3, minus 4 by 5 and so on. And as you can see here, this is a monotonically decreasing sequence, right. So again we have a monotone subsequences for every real sequence. Consider the sequence minus 1 by power n. So we have all look for this. This is the alternate type of sequences, right. So minus 1 1, minus 1 1 1 1 1, and look at the even index terms. All the even index term are a constant term and constant term is 1, right. Similarly all the odd index terms, so this is minus 1, minus 1, minus 1, minus 1 and so on. This is also a constant. Every constant sequence or subsequences are either monotonically, we can say the monotone increasing or monotone decreasing, but cannot say that monotonic strictly monotone increasing or monotone decreasing, right? So, 1 is a constant sequence and this is a monotone sequence. Similarly, -1 is a constant sequence and it also says that it is a monotone sequence. But remember this one, we cannot say for a constant sequence a strictly monotone increasing or strictly monotone decreasing. Now, based on these theorems and examples, we do understand that a sequence containing the real numbers may have the monotone subsequences. These are the base for the Bolzano-Weierstrass theorem. To develop the Bolzano-Weierstrass theorem, we need those theorems. So, what the theorem says that every bounded sequence Xn of real numbers has a limit point, right? So, that is the theorem. What it says, every bounded sequence Xn has a limit point. Suppose Xn is a bounded sequence and X belongs to, X is the collections of Xn, N belongs to natural number. So, that is the written as, and capital X be its range. So, range set and all those set we have already done this, right. So, Xn is a bounded sequence and X be its range, right. Why we are looking for this range? So, if you are not remembering, then I will give you one of the most striking examples why range is important is like this, right. So, this is a sequence and this sequence how many terms it has? It has infinite number of terms, but what will be the range set of this set? Range set is nothing but it is a only 2 terms, only 2 things, right, -1 and 1, the 2 elements are there in a range set. Similarly, any constant sequence, so suppose we have a constant sequence C, right, and how many terms it has? It has C, 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 C and C, right, infinite number of terms in that sequence. And what will be the range set? Range set is the singleton set C, the only single element C containing the range set, making the range set. That's why we have to consider the range set as a different than the sequence terms, right. So, now I think this will help you why we are considering capital X as the range set. And remember, the element of the range must be the element of the sequence itself, isn't it? See here, I have written the distinct elements of the sequence in the range set, that's all. So, since the sequence is bounded, therefore, its range set X is also bounded, as you can see here. And there are 2 possibilities for this, either capital X is finite or capital X is not finite, that means infinite. So, we will explore both these possibilities. The first one is X is finite. So, now consider if range set X, remember this one, X is the range set, and why we have chosen, you understand, right. So, capital X is finite, then there must exist at least one member epsilon, let us say epsilon, of this range set capital X, such that Xn is that element, because range, every element of the range set is the element of that sequence. So, for an infinite number of values of n, right. This means that every neighborhood epsilon minus is epsilon is of epsilon contains Xn for an infinite number of values of n, right. So, thus epsilon become a limit point of the sequence Xn. Look at this one. So, 1 and -1 become a limit point of this sequence, right. Similarly, we consider X is infinite. Since it is bounded, it has by Bolzano-Weierstrass theorem that it has at least one limit point, and let that limit point is 0 here, right, or sigma here. So, again, since sigma is the limit point of capital X, limit point of this capital X is the range set, capital is the range set. Therefore, every neighborhood, that means epsilon minus epsilon plus epsilon, this is the open interval, right. for an infinite number of values containing that point epsilon, and therefore epsilon become a limit point of the sequence section. The converse of the theorem is not always true, for there do exist unbounded sequences having only one real point. Example is something 1, 2, 1, 4, 1, 6 and so on, has a unique limit point 1, but it is not bounded above. So what the Bolzano-Weierstrass theorem says, the converse may not true. So every bounded sequence has a limit point. That's the Bolzano-Weierstrass theorem, and it is a very bold statement in the real analysis. But the converse may not true, as we have seen here. That taking one example as every odd index number is a constant 1, 1, 1, 1, 1, and then for an even index it's increasing 2, 4, 6 and 8 and so on. So that will make that this has a unique limit point, but it is not bounded above. So a sequence may have a limit point, but it may not bounded above or bounded below. So look at some examples. Consider the sequence xn equal to -1 by power n. It is a bounded sequence, and what will be the limit points? So -1, 1, -1, 1, -1, 1, -1, 1 and so on, right? What will be the range set? The range set containing only two elements, -1 to 1. So range set is a finite set here. Range set is a finite set here. This is the range set. This is the range set. Range set is a finite here. And how many limit points it has? The sequence. So obviously the sequence repeated -1, -1 how many times? Infinite times, and 1, 1, 1 and infinite times. So 1 and -1 both becomes the limit points of the sequence, bounded sequence -1 by power n, right? Consider the sequence 1 beta n. It is a bounded sequence, bounding between what? Bounding between 0 to 1, right? And 0 to 1, 0 to 1, because it is 1, 1 by 2, 1 by 3, 1 by 4 and so on. So what will be the range set? Can you imagine what will be the range set? Obviously you can. Range set are nothing but containing all those elements here. So range set x containing 1, 1 by 2, the whole xn here. So what will be the limit points? It is a bounded sequence and bounding between 0 and 1. What will be the limit point? Limit point is nothing where it's converging to 0, and if a sequence is converges to a point, then it converges uniquely. So it has only unique limit point. That means it has only one limit point, and henceforth this sequence has 0 as the only one limit point, not at all. Consider the sequence 1, 0, 1, 0, 1, 0. This is the alternating type of the sequence where the alternate terms are repeating, 1, 1, 1, 1 alternating positions and 0, 0 at the alternating position. This is the bounded sequence, and what will be the bound it has? It has a bound 0 and 1. So how many limit points of that sequence exist? There are two limit points occurs, 0 and 1. So here are 0 and 1 are two limit points of that sequences. Now example 4. Consider a sequence √2 - 1 by n. Obviously let us explore this sequence. So as we understood, √2 minus of 1, √2 minus of 1 by 2, √2 minus of 1 by 3 and so on, right? So focus on 1 by n. 1 by is a converging subsequence. This is converges to 0. That means the whole this one is a bounded sequence. And how much the bound it has? It is a bounded sequence having a √2. So √2 is the only limit point of that sequence. Why? Because 1 by n is converging sequences and converges to where? 0. So it also converging and converges to where? √2. So √2 is the unique limit point of this sequence, and it is a bounded sequence. Consider the sequence xn -1 by power n n. It is a bounded sequence, and where it bounds. So let's do some calculations. So firstly explore this. So first term is minus 1 by 1 minus 1 by 2 minus 1 by 3 1 by 4 minus 1 by 5 1 by 6 minus 1 by 7 and so on, right. Now look at the bonds. The lower bond is going to be minus 1. What will be the upper bond? Can you imagine this one? 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6 and so on. So it is a bounded sequence, bounded between 1 and minus 1, and henceforth their limit points are 1 and minus 1. Consider the sequence 1 plus 1 by n. 1 plus 1 1 by n is a bounded sequence as 1 by n bounded between 0 to 1, 0 to 1, 1 by n, 0 to 1. Henceforth the whole sequence is bounded sequence and bounded between where? Is to 1 and 2. But what will be the limit points? For the limiting point, consider on this 1 by n. 1 by n where it converges to 0. So the whole sequences converges to where? Converges to 1 plus of 0. So this will be the converging point. So 1 is the answer. So 1 is the limit point, and this sequence is a converging sequences. Now look at for example 5. Consider a subsequence minus 1 by power n plus 1 beta n, and is this a bounded sequence? Obviously it is a bounded sequence. And what will be the bounds for that? Now you can explore this subsequences. So this is minus 1 plus of 1, right. So this is equal to 0, and the second term minus 1 power square, that is equal to 1 plus of 1 by 2 is equal to 3 by 2. This is 3 by 2, and the third term is minus 1 plus of 1 by 3 plus of 1 by 3. So this will gives you minus of 2 by 3 and so on, right. So in the previous slides we have seen all those things. Now what will be the bonds? It is bounded between now you can see here, this is the 0 is 1 point and 3 by 2 and 1 by 2 and so on. So it's a bounded sequence. Maximum is something here. So and is a bounded sequence. And how many limits points? The limits points we can explore this limits points. Minus 1 and 1 are the two limits points. So why? Because 1 beta n converges to where? 0, and minus 1 by power n converging to minus 1 and 1 both. So that means these makes whole sequence have those two limits points, different two limits points, minus 1 and 1, right. Remember this one. So this is the idea that you have to move across with a given bounded sequence. If it is a bounded sequence, it must have some limits points, and the vice versa, that means a sequence may have a limit point, but it may not be a bounded sequence. Consider the sequence sine n pi by 2, and obviously it is a bounded sequence. Why? Because it lies between minus 1 sine of theta lying between minus 1 to 1, right. So look at this one. So sine of theta always lying between minus 1 to 1, right? So as you can see here, this is the sine theta, and what will be the value? This is 1 and minus 1, and this is 0, this is pi, this is 2 pi, right, this is pi by 2, right, and this is 3 pi by 2, 3 pi by 2 and so on, right. So sine n pi by 2 is a particular case of this sine theta. So it also lies, so sine pi by 2, sine n pi by 2, we can see that it also lies between minus 1 to 1, the peculiar things, right. So you can have the, I mean actually it has this type of things, right. So you can have this n pi n equal to 1, you have a pi by 2, n equal to 2, you have a pi here and so on, right. So how many terms are infinitely repeated to each other? So look at here. So if you put this one, this is the 0. So this is for n equal to 2. And for n equal to 1, you have n pi by 2. So that means you have 1. So you got 1 as a number, you got 0 as a number, you got 3 pi by 2, that means you have a minus 1, and then again repeating like this, you have a 0 here, right, 0 here, then you have a 1, then you have a minus 1, then a 0 and so on. So how many terms are repeating infinitely? There are 3 terms which are repeatedly infinitely, that is minus 1, 0 and 1. And all these 3 terms become a limit points of the sequence sin n pi by 2. So this is one important limit points using the Bolzano-Weierstrass theorem to find for the given sequence sin n pi by 2. Similarly, can you explore for a sequence 5 minus 1 by n? Obviously 1 by n is going to be where? Is going to be 0. It is a bounded sequence, and how many points it has? It is a converging, moreover it is a converging sequence. Every converging sequence is a bounded sequence and converges uniquely. So 5 minus 1 by n is also converging and converges uniquely to the limits points 5. So 5, right. So I believe you can also find out this limits point something like n tends to infinity 5 minus 1 by n, which can be written as limit n tends to infinity 5 minus of limit n tends to infinity 1 by n. So this will be going to be 5 minus 0 equal to 5, right. So this is a uniquely converging sequences, and it has a unique limit point 5. So these are the all examples. I think this is enough to explore Bolzano-Weierstrass theorem, its applications in using finding out the boundedness of a sequence, and if it is bounded, then the limits points and so on. So thank you so much.